In this video, we solve problem 12.3.036 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use the model for projectile motion, assuming that there's no air resistance and that gravity is 32 feet per second squared. The problem statement says a bomber is flying at an altitude of 30,000 feet at a speed of v equals 480 miles per hour, see figure. And so they have this plane here. They show that its velocity is completely horizontal, parallel to the ground. It's going in this direction off to the right with a magnitude of 480 miles per hour, and that plane is 30,000 feet up in the air. Now, that plane is a bomber, and it's going to drop something. It's going to drop a projectile, and then it has to hit the target at some point. Then the question says, when should the bomb be released for it to hit the target? Now, when I hear the word when, I think time. But this time they're not actually asking for time. They're asking us to give our answer in terms of the angle of depression from the plane to the target. Now, the angle of depression is the angle that we make if you take a line that's parallel to that plane, and then you have a line segment that goes from the plane to the target. It's that angle from that horizontal with the plane down to that line segment from the plane to the target. That's the angle of depression. That's what they want. They ask us to round our answer to 2 decimal places, and they have this little degree symbol, so we know we want our answer in degrees. Then the second part of the question says, what is the speed of the bomb at the time of impact? Round your answer to the nearest whole number, and we know we want our answer in miles per hour. Okay, so one way that you could handle this is you could just find the model for projectile motion in your book and just identify all the variables and then just sort of substitute and use that to come up with the equations. I would rather not do that. I'd rather that we derive our formulas for x as a function of time and y as a function of time from first principles. So we'll do that. If you're not interested in doing that, you can always skip over this part in the video. Now, in order to solve this problem or find the equations for x as a function of time and y as a function of time from first principles, we need to find initial acceleration in the x and y direction, initial velocity in the x and y direction, and the initial position in the x and y direction. Now, if you're saying to yourself, why do we need x as a function of time and y as a function of time again? It's because we're trying to answer this question of when should the bomb be released in order for that bomb to hit the target. Now, answering that question is about finding that angle, and finding that angle involves knowing how far we've gone in the x direction as that bomb is leaving the plane and going towards the target. We need to know, like, what is that horizontal distance from there to there? And we also need to know the vertical distance. Well, we can tell that the vertical distance is going to be 30,000 feet, right? The question is, if I want to find theta, well, how am I going to find it? Well, I need the y distance that was dropped, and I need that x distance that was dropped. So I need to find x as a function of time in order to answer this question. So let's find x and y as functions of time from first principles. Now, this coordinate system that I've drawn on this picture was not initially on the picture. You can put the origin 0, 0 wherever you want. For simplicity, though, I chose to put my origin right here so that my initial x value would be 0. So the plane is initially at x equals 0, and the plane is initially at y equals 30,000 feet. I made the positive x direction to the right and the positive y direction going straight up, just like we're accustomed to in pre-calculus type classes. Okay, so let's write down everything that's given and then use that given information to derive the formulas for position in the x direction as a function of time and position in the y direction as a function of time. Now, because we're splitting everything into an x direction and y direction, it makes sense to organize our information in that way as well. So we should organize our given information according to whether we're looking at the x direction or the y direction. Let's say organizing it in terms of x and y. Like, you guys know what I mean, but it's kind of hard to articulate it sometimes. All right, so what do we know? I'm going to put my x information over here, and I'll put my y information on the other side. Well, we know that the acceleration due to gravity goes straight down and has a magnitude of 32 feet per second squared. Now, since it's going straight down, that's in the y direction only. So there's no acceleration in the x direction. And the acceleration in the y direction is a negative 32 feet per second squared, because we're treating this as the positive y direction. So based on our choice, this is acceleration in the y direction is negative 32 feet per second squared. Now remember, acceleration from calculus 1 is the second derivative of the position function with respect to time. So if y of t represents position at time t, y double prime of t would be the acceleration. So y double prime of t is negative 32 feet per second squared. And the acceleration in the x direction is 0, because there's no acceleration in the x direction at all. Now we want to find, let's say, velocity. Well, velocity in the y direction is going to change because we've got an acceleration in the y direction. So maybe we can't find velocity in the y direction in general, not yet, but we can look for the velocity in the y direction at time t equals 0. So velocity in the y direction in general is just represented by y prime. If y of t represents position, at time t equals 0, we'd call that y prime of 0. So now let's look at our picture. That plane is not flying up or down. It's going horizontally, parallel to the ground. So there is no velocity in the y direction at time t equals 0. Eventually there is a velocity in the y direction, but that's only due to the acceleration due to gravity. But initially, acceleration or velocity in the y direction is 0. Since our acceleration was measured in feet per second squared, we will want this velocity in feet per second. Okay, now velocity in the x direction at time t equals 0 is 480 miles per hour. Now you want to be very careful here. The units that we're using for x and the units that we're using for y are different. Here we're measuring distances in miles and times in hours. Here we're measuring distances in feet and times in seconds. We want to keep track of all of that. And then we want initial position in the x direction and the y direction. So that's going to give us x of 0 and y of 0. Now, based on our choice of coordinate system, when time t equals 0, x is equal to 0, because I just chose for my x equals 0 to be directly below the plane. And since this is in miles per hour, I'll have x in miles. And that would make the second derivative in 0 miles per hour, so miles per hour squared. And the initial position in the y direction is 30,000 feet. And this number of feet is consistent with the units that we already have up here. Okay, so we have the acceleration functions as functions of time, both in the x direction and y direction. Since there's no air resistance, if we want to find x as a function of t and y as a function of t, all we have to do is anti-differentiate twice, and we can find those functions. And then this should just be a single prime, not a double prime. Then whenever we anti-differentiate twice, we're going to have two constants of integration for this one and for this one. These initial conditions, x prime of 0 equals this number. x of 0 equals this number, and y prime of 0 equals this number, and y of 0 equals that number. Those are all going to, excuse me, give us the values of those constants of integration. So let's look at each of these separately. If I have x double prime is equal to 0, and I want x prime, all I have to do is anti-differentiate with respect to time. The antiderivative of 0 with respect to time is a constant. So now we have x prime of t is equal to a constant. And then we're also told that x prime of 0 is equal to 480 miles per hour. Hopefully you see that if x prime, the velocity is constant and the initial velocity is 480 miles per hour, you know that that constant must be 480 miles per hour. And hopefully you see that. But if you don't, in general, the way you would find the value of c is you'd substitute t equals 0 here. And then you would substitute it on the right-hand side as well. Now there is no t over here, so we just get c1. And then you would set this result equal to whatever we have in the initial condition. X prime of 0 is going to be c1 no matter what. Now we're told that x prime of 0 is 480 miles per hour. And then you solve for c1, which just means that c1 is 480 miles per hour. So now we have that velocity in the x direction is a constant 480 miles per hour. And I think that makes sense. If we're not accelerating in the x direction at all, we're not speeding up or slowing down in the x direction at all, we start out going 480 miles per hour, we should continue to go 480 miles per hour. Okay, so if we want to find position as a function of time, and we have the derivative of position or velocity, we can anti-differentiate again with respect to time. The antiderivative of 480 with respect to time is 480t. We're going to add a constant of integration. But we don't want a position function with an arbitrary constant in it. To find c2, we're going to use this initial condition. So this says when t equals 0, our initial x position is 0. Just based on our choice of coordinate system, our choice of the origin. And if we simplify this, x of 0 is just c2. Then you set that result equal to the what you know x of 0 to be, which happens to be 0 miles. And then you solve for c2. Well, that means c2 must be 0. So now we have x as a function of time. It's just 480t plus c2, which is 0, so it's just 480t. But be careful here. X is distance in the x direction, excuse me. But this is 480 miles per hour times the number of hours. Mm-hmm. So this is in miles. And t is time elapsed since we dropped the bomb. And if that's in miles per hour and we're multiplying by hours, t is measured in hours. So you want to keep that in mind as you move forward, that's a very simple formula, but we need to keep track of the units, especially because the units are different in the y direction. Okay, so we solved that differential equation initial value problem for x of t. Great. We're going to do the same thing over here for y. We know y double prime of t is negative 32 feet per second squared. So if we want y prime, we take the antiderivative. And we'll have a constant of integration. I already used c1 and c2, so I'll call that c3. So now I have y prime of t is negative 32 times t plus c3. This is going to be in feet per second. But I don't want this arbitrary constant. In order to find the value of the arbitrary constant, I use the initial condition for velocity. So basically, I substitute in t equals 0, and then I simplify. Y prime of 0 would be c3, no matter what, given that initial or that known constant acceleration. But then we say we have more information. We know that y prime of 0 is 0, so we can set this result equal to the value of y prime we have up there, and then we solve for C3. Well, it's really easy. C3 must be 0. So that means that y prime of t is equal to negative 32t, again, in feet per second. All right, we're trying to find position in the y direction as a function of time. We've got the derivative. To find position, we anti-differentiate again. So we add 1 to the exponent, divide by the new exponent. Don't forget your constant of integration. So that's y of t, but it's got an arbitrary constant in it. It's not very helpful for us as a position function if it's got an arbitrary constant in it. So we'll use this initial condition to find the value of c sub 4. Replace t with 0. Now we know that initially our y position was 30,000 feet. So this simplifies to C4. I'm going to set that equal to 30,000 feet and solve for C4. Well, that's a simple equation. C4 must be 30,000 feet. So y is given by this function where C4 is replaced by 30,000 feet, just like x was given by this function where C2 was replaced by 0. So y of t is negative 16t squared plus C4, which is 30,000, and y is distance traveled in the y direction, or actually not distance traveled, this is more position in the y direction. And I guess this is distance traveled in the x direction, but it's also position in the x direction, given our choice of origin. But here, position and distance traveled are not the same thing. So we've got our position in the y direction, and this is in feet. Those units matter. And t is time elapsed since we dropped the bomb. And time is measured in seconds here. Okay, so we've got x of t and y of t. We're good. All right, now our hope is that these two functions are going to allow us to answer the question that they asked us. So the question says, when should the bomb be released for it to hit the target? You might think, I don't have enough information. All I know is that we're going at a speed of 480 miles per hour, and we initially started at 30,000 feet, and then it's just going to hit the ground. Like, how do I know when it hits the ground? Well, we have enough information, but it's sort of implied. If we're on the ground, that y value is going to equal 0. So if they just asked me when should the bomb be released for it to hit the target, and I saw the word when and I was looking for time, what I would do is I would set y equal to 0 and solve for t. So let's do that. So we're going to find the time elapsed between, we're finding the time elapsed between when the bomb left the plane and when it hit the ground. And the way that we do that is we're setting y equal to 0 and solving for t. So we have 0 equals negative 16t squared plus 30,000. I'm going to subtract the 30,000 from both sides, divide both sides by negative 16, and then t would be plus or minus the square root of this quotient if we were just solving the algebra problem. but we know we're going forward in time. So we want the positive time value. This is 3 times 10,000. So that's 3 times 100 squared over 4 squared. So we're going to have 100 square root of 3 over 4. And that is 25 square roots of 3. Now careful. This is the time elapsed in seconds. 25 square roots of 3 seconds. And if we want an actual number of seconds, we can, well, that's the exact number of seconds. We get a decimal approximation of approximately 43.3 seconds. And that's not what they asked us for, though. What we were asked for is the angle of depression from the plane to the target. We're asked to round to 2 decimal places. In order to find that angle of depression, I need to know this distance that we traveled in the x direction from the time that bomb left the plane to the time the bomb hit the ground. I need that distance and this distance. Now we know that this distance is 30,000 feet. We don't know the distance traveled in the x direction over that time period. But now we know how much time has elapsed. Since we know how much time has elapsed and we know how x varies with time, we can figure out what that distance traveled in the x direction was. And once we know the x, or the distance traveled in the x direction, we already know the distance traveled in the y direction, and we can just use the tangent function. Tangent of theta is y over x in order to find theta. So it's not too bad, just have to be careful. When we use this function here, t needs to be measured in hours, not in seconds. So we're gonna have to do a little bit of dimensional analysis to convert from seconds to hours. So let's do that. Whenever I see this, I always think of that book, The Martian. Anytime I do dimensional analysis, I think of The Martian. There's a lot of dimensional analysis on that book, and so how he's counting all the potatoes, how many potatoes he can grow and how long he can sort of last on Mars, given all of his resources. It's just a lot of unit conversions, a lot of multiplication. So we're trying to get from seconds to hours. In order to do that, we need to convert out of seconds and into hours, but I think it's easier to convert out of seconds and into minutes, and then convert out of minutes and into hours. We know that there are 60 seconds in a minute, and we know that there are 60 minutes in an hour. So if we multiply straight across with this, the seconds reduce here, the minutes reduce here, and we'll have a number of hours that remain. And that's exactly what you want. If you're trying to decide how to set up the dimensional analysis, you just put the units that you're trying to get rid of in the denominator, and you put the units that you're trying to get to in the numerator. And if there's not a direct conversion, there is clearly a direct conversion between seconds and hours. But if there's some intermediate conversion, like you'd like to go from seconds to minutes and then minutes to hours, you just use each of those repeatedly, like I did. And then eventually you'll get to the units that you want. So we've got about 43.3 seconds, which is exactly 25 times the square root of 3 seconds. So we'll have 25 times the square root of 3 times 1 hours divided by 3,600. And then 25 goes into 3,600. Let's see how many times. 144. So if we simplify this, or if we want to simplify this, we can call this square root of 3 over 144 hours. All right, now that I know how much time has elapsed in hours, I can substitute that in up here, and then I can find the distance traveled in the x direction in miles. So let's do that. And I'm using this exact answer rather than the decimal approximation because I don't want to use estimated values and then carry those
errors forward from part of the problem to part of the problem. We know that WebAssign is finicky. We know that if we're off by 100th, that WebAssign will say we're wrong. So I'd like to just round at the very end of the problem if possible. So we're substituting t equals this many hours into the formula for x. That'll tell us how far we've traveled in the x direction, or how far that plane has traveled in the x direction as the bomb started at the plane and then hit the ground. And if we multiply those guys together, we have 480 divided by 144. That's 10 over 3 times the square root of 3. And that's some number of miles. But remember what our picture looked like. This is 30,000 feet. And we've got a plane that's right here, and then it's dropping a bomb. And we're saying, of course, this is not to scale, that this distance that we traveled in the x direction is 10 times the square root of 3 over 3 miles. And if you want to know approximately how many miles that is, you can always find a decimal approximation. So about 5.77 miles. But again, this is miles and that's feet. We need to have the same units if we want that angle of depression that we were asked for. So we've got a couple of options. If we're trying to find the angle of depression, we can either convert these miles to feet, or we can convert these feet to miles. We need the same number of units so that the tangent of theta is equal to this over this. It's a ratio, it's a unitless ratio. We need them both to be in miles and the miles to cancel out in order to get the right angle. So they both need to be in miles, or they both need to be in feet. I think I'd rather convert from miles to feet rather than feet to miles. So let's take this and convert to miles, or excuse me, to feet. 1 mile happens to be 5,280 feet. Now, if you didn't know that conversion factor, that's okay. You just look it up. I would Google it. Just say 1 mile is this many feet, and it just pops right up. And 5,280 is divisible by 3. So let's find out what that is. Oops. So we have 1760. So you have 17,600, because that's, I'm multiplying the 760 by 10 times the square root of 3. That's a number of feet. If you want an approximate value, that's 30,484.09 feet. Again, I'm going to use the exact answer when I'm solving for that theta, but getting the decimal approximation is helpful because then I can think about whether theta is reasonable. If this is 30,000 feet, and this is approximately 30,484 feet, well, those are about the same. So I'm expecting an angle that is about 45 degrees. It's not going to be exactly 45 degrees because that's not 30,000 and 30,000 exactly, but it's close. So now if I want to find theta, I will just use the tangent function. Tangent of theta is opposite over adjacent. Excuse me, the opposite side is 30,000. The adjacent side is exactly 17,600. Times the square root of 3 feet. The feet reduce, and now you just have tangent of theta equals this ratio. It's a unitless ratio, which is exactly what we want. And then that simplifies. We've got 300 over 700, or 176 is 75 over 44, and there's still a square root of 3 in the denominator. So if I want to get theta by itself, I need to take the inverse tangent of both sides, because the inverse tangent of the tangent gives you the original. Actually, I think I'll show that step. And this simplified to 75 over 44 times the square root of 3. It kind of looks like you're multiplying, but it's not multiplication. I really want you to think of that as a composite function. You're nesting one function inside another function. You're taking the inverse tangent of this, and the inverse tangent of the tangent of theta is theta. And then we get that back, provided that theta is within a certain range. But anyway, for our purposes, this is fine. So theta is the inverse tangent of this. And we'll use our calculator. And again, because of this value and this value, we're expecting an angle close to 45 degrees. Make sure you're in degree mode because we want answers in degrees. We get about 44.54 degrees. All right. Now that is not the answer to the whole question. That's the answer to the first question, but it's not the answer to the entire problem. So let's go back to the original problem statement. It asks, when should the bomb be released for it to hit the target? And they're not actually asking for a time, they're asking for an angle of depression. We just found that to be 44.54 degrees, which is about 45 degrees, which is what we expected. And now we want the speed of the bomb at the time of impact for us to round to the nearest whole number, and we want speed in miles per hour. Okay, now in order to find speed, first we need to find velocity. This is our strategy. So we want to find the velocity at time of impact. So that means we need speed in the x direction and speed in the y direction at that time. And notice that we want our results in miles per hour. So we want both of these in miles per hour. And then once we have the magnitude of the velocity in the x direction and the y direction, because we've got some bomb, it's sort of hitting the ground like this, right? It's got an x component and a y component. That's its velocity. In order to find the speed, we just take the magnitude of the velocity. Okay, now our speed in the x direction is constant. Now remember, our velocity in the x direction was 480 miles per hour, regardless of what time was. So at the point of impact, it's still going to be 480 miles per hour. So that is already in the right number, or in the appropriate units. So we're good to go there. Now for y prime, we've got negative 32 times t, but remember with y prime, we're measuring distance in feet and time in seconds. So the time that we need to use here to get velocity in the y direction is going to give us, or it has to be in seconds so that we can get a number of feet per second. And then we're going to have to convert from feet per second to miles per hour, doing a little bit of dimensional analysis once again. Okay, so let's do that. Now this picture that I've drawn here is not to scale, obviously, but the velocity in the x direction is 480 miles per hour. to find the velocity in the y direction, we go up to our velocity in the y direction formula, make note of the units, that's feet per second, and then we substitute in the time of impact. Now the time of impact we found a while ago, it was 25 times the square root of 3 seconds, or approximately 43.3 seconds. So since we are using units of feet per second here, we want time in seconds here. So we're going to substitute 25 times the square root of 3 seconds. And this is a number of feet per second squared times a number of seconds. So we're going to get a number of feet per second when we're done. So you have negative 800 square roots of 3 feet per second. Now the fact that that's negative just means that that velocity is pointing down in the y direction. And we kind of already knew that. This is negative 800 square root of 3 feet per second. But again, we want, here's our problem statement, the speed of the bomb at time of impact in miles per hour. So that means we want velocity in the x direction in miles per hour, velocity in the y direction in miles per hour. And right now we've got a number of feet per second. So we're going to have to do a little bit of dimensional analysis like we see Matt Damon do in The Martian. Or if you read the book was really good. They took a lot of the just hilarious like personality of that character out of the movie. I think they were trying to be more serious when they made the movie, but I laughed out loud a lot while reading The Martian. That was a super fun book. Okay, so we want to convert to miles per hour. Well, we can first get rid of feet and go into miles, and then get rid of seconds and go into hours. If we want to get rid of feet and go into miles, we want the ratio to look like that so that the feet reduce. And we know that 1 mile is 5,280 feet. If you don't know that, you can always look it up, just Google it. Okay, and now we have miles per second, but we want miles per hour, so we need to get rid of the seconds. And so I'll go from seconds to minutes, and I don't want minutes, so I'll get rid of the minutes and go to the hours. There are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. So when we multiply, the seconds reduce and the minutes reduce, and now we have a number of miles per hour. Good. Okay, so we're going to get negative 800 square roots of 3 times this 3,600 over here. I think I'll just do the negative 800 times 3,600. So negative 2,880,000 times square root of 3 miles, all divided by 5,280. Let's see if that simplifies. And that's a number of hours. And so we end up with negative 6,000 square roots of 3 over 11 miles per hour. I was just simplifying that, and I had to tack on that square root of 3. You want to multiply by the square root of 3 to get a decimal approximation. You have a velocity in the y direction of approximately negative 944.75 miles per hour. So we've got 480 there, and about negative 944.75 miles per hour over here. But again, we want to use the exact answers because we know WebAssign is finicky. So we're going to use not that one, but the exact answer in miles per hour, which is that negative 6,000 square roots of 3 over 11. Okay, so our velocity vector at time of impact has an x component of 480 miles per hour and a y component of negative 6,000 square roots of 3 over 11 miles per hour. And if I want the speed, I just take the magnitude of that. So you take the components, you square them, you add them, you take the square root. Easy breezy. So we're squaring a negative number so that it really doesn't, we don't even need to type it in. Got that number, we're going to square it. Then we're going to add 480 miles per hour squared. And then we're going to take the square root of the answer. And we get about 1,059.699. And that is about 1,060 miles per hour when we round to the nearest whole number. Yes, round to the nearest whole number. Okay, so that's how we do that. You want to be very careful as you're solving a problem like this because of the units. We've got all of the units in the y direction, distance is measured in feet and times in seconds, and in the x directions, distances are measured in miles and times in hours. But when we put all of those pieces together, it's really not too bad. You just have to remember what the units are of the particular function that you're working with. I hope that helps. Let me know if you have any questions.